Hello friends, welcome to this session. Today I will try to explain you the behavior of SCR on the basis of two-transistor model. So we can explain turning on mechanism of SCR by considering SCR made up of two transistor, and that's why it is called as two-transistor model or two-transistor analogy for SCR. You know that SCR has a four regions P, N, P, N. It has a three junction and three terminals. So this is anode, this is cathode, and P region close to cathode is gate. Now let us cut this SCR in this way and redraw the structure. So how we get I can draw this way. So we have this first P region, then second N region and P region, and here this and this last N region. So this is P, N, P, N, P, N, and imagine that they are interconnected. So this is your cathode, this is anode, and this is gate. See that SCR, when I cut it here, I get a structure like this. See this structure P and P, three region, two junctions. So this will constitute one transistor T1, PNP transistor. And then we have NPN. This will work as a transistor T2. So we can think this SCR made up of two transistors. Now in order to explain and get some expression for anode current, and on the basis of that we can explain its behavior. So let us draw the circuit for this. So circuit for this would be like this. So let us consider this as a transistor 1. P and P. And this is NP. So this is a anode, cathode, and gate. If you look at the SCR using the symbol, we have three terminals. This is anode, this is a cathode, and this is gate. Then if there is anode current, so current entering here, it will be anode current. Current leaving this cathode will be, say, cathode current, and small gate current injected here, it will be, say, Ig. Right. So you can see that current entering, small gate current injected, that makes IK, cathode current, right? Now if you look inside of the SCR, so this is nothing but, externally it is anode current, but internally this is nothing but emitter current for this transistor 1. So the transistor 1 T1 having common base current in alpha 1, and the other transistor, let us call it as T2, which has common base current gain alpha 2. This will be the current coming out of the base. This is a PNP transistor, and therefore we will call this as IB1. Look at this. The base of first transistor is connected to the collector of the second, and therefore this is nothing but AC2. Here also the collector of the first transistor is connected to the base of second transistor, and therefore the collector current here, this is AC1. The current which we are going to inject is the gate current, and that is nothing but base current for the second transistor. And the current leaving the SCR, just we have seen it is a cathode current, but this is also emitter current for second transistor. See that here the collector of second transistor is connected to the base of first transistor, and collector of the first transistor is connected to the base of second transistor. So there is a sort of feedback, right? Actually, in short, this action can be described as when small gate current is injected, that will increase the collector current of this transistor, that increases the base current of the first transistor, that will increase collector current of the first transistor, which is nothing but the base current for second transistor, and so on. There is a cumulative action, we call it as a regenerative action, and because of that both of these transistor goes into saturation, and we get a large collector current and this cathode current or emitter current, and you say that SCR is fired. As this transistor goes into saturation, the voltage across them drops to very low value, and that's why when SCR turns on, anode to cathode voltage drops to just 1 to 5 volt. Now let us get some useful equation. Our goal is to get derivation for anode currents. So to begin with, we have from this diagram, see here IB1 is nothing but IC2. So we can write straight away IB1 equal to IC2. So let us call this as equation 1. Similarly, from this diagram, this I can write the cathode current for SCR is nothing but sum of anode current and gate current. So you can write sum of gate current and anode current. So this is the second equation. Then this base current also can be expressed as, you know that for a transistor emitter current is given by base current plus collector current, and from this you can have IB as IE minus IC. So using this equivalence for transistor in this, so IB1 I can express as IE1 minus IC1. So let us call this as expression 3. But we also know that the collector current for any particular transistor can be expressed as alpha into IE plus ICO. What is this alpha? Alpha is common base current gain, and we have defined it as ratio of IC to IE. for a transistor. Okay. Uh, Collector current is expressed as alpha into emitter current plus ICO, where ICO is the reverse leakage current at reverse bias collector junction, and this is a very small, negligibly small, and therefore we are going to ignore it. And therefore this expression for transistor 1, I can write this as IC1 will be equal to alpha 1 into I1. So let us call this as equation 4. So we have IC1 equal to alpha 1 into I1. Use this expression here. So equation 3 will be IB1 is equal to IE1 minus IC1. For IC1 I am replacing this alpha 1 I1. So from this expression you can take out I1 common. So in this way IB1 can be expressed as IU1 into bracket 1 minus alpha 1, right? But look at this diagram. I1 is nothing but the anode current. So this I1 is equal to IA, and therefore the expression for the base current for transistor 1 is IA into 1 minus alpha 1. So let us call this as equation 5. So you got here IB1, and similarly we want to find out expression for IC2. So on the same basis we can have IC2 can be expressed as on this same line. IC1 is expressed as alpha 1 into IE1. So IC2 can be expressed as alpha 2 into IE2, right? But emitter current of second transistor, look here, emitter current of second transistor is nothing but the cathode current. So I can write IC2 as alpha 2 into cathode current. So let us call this as equation 6. Now equation 5 is for IB1 and equation 6 is for IC2. So use this value of IB1 and IC2 in equation number 1, and what we get is that on left hand side this IB1 equal to IC2. So on left hand side we have IB1, so IB1 can be expressed as IA into 1 minus alpha 1, that is equal to IC2, and we have here IC2 this. So IC2 is alpha 2 into IK. But again IK can be substituted as, look here, IK can be substituted as IG plus IA, right, from equation 2. So IK is nothing but, cathode current is nothing but gate current plus anode current. So using this value here, so what we get is 1 minus alpha 1 equal to alpha 2, replace this IG plus anode current, expand this bracket 1 minus alpha 1 equal to alpha 2 IG plus alpha 2 IA. Then rearrange the term, bring all the IA terms to left hand side. If I bring it IA into 1 minus alpha 1 minus of alpha 2 into IA, that is equal to alpha 2 into Ig. Right, now from here I can have IA as a common factor, so into bracket we are left with alpha 1 minus alpha 2, on right hand side alpha 2 into Ig, and therefore the expression for anode current will be alpha 2 Ig upon 1 minus alpha 1 minus alpha 2, or to make it simple, IE equal to alpha 2 to Ig upon 1 minus alpha 1 plus alpha 2. Right, so this is the expression for anode current. Now look at this expression. So when there is a zero gate current, so this expression will be just zero, no anode current, no question of anode current. But when you just insert a small Ig, as Ig increases, from this diagram you can see that as Ig increases, that increases the IC2, that increases IB1, then IC1, and so on, and therefore anode current increases. So this increases IC2, this increases IC1, once again IB2, and in this way the collector current and finally anode current increases. And you know one thing, as anode current increases, actually this anode current increases because of the alpha 1 and alpha 2 also increases with the increase in collector current and emitter current. But you know that as anode current increases, and when it increases above latching current, what happens? SCR turns on. Latching current is the minimum anode current required for SCR to go from off state to on state guaranteed. And you also know that once SCR fires, this gate current has nothing to do with that afterwards, of course. So once SCR fires, gate current loses its control on SCR state. So this is important. And once again, you know that so long this anode current is above holding current, SCR remains on. So this is how you get expression for the anode current by considering SCR to be made up of two transistors. Now look at this denominator. When small Ig is injected, it increases the alpha 1 and alpha 2, and if their sum, their value increases and approaches to 1. What is the denominator here? 1 minus alpha 1 plus alpha 2. As this approaches to 1, the value of this denominator becomes that tends to 0, and mathematically when anything upon 0, that makes this infinity. So that increases anode current by large amount, and what we need is just it should be above the latching current, and once anode current crosses the latching current, SCR turns off guaranteed. So this is very important, and this is the main factor utilized for turning on the SCRs. So this alpha 1 plus alpha 2 can be made equal to 1 by different techniques. What are the techniques? By increasing the temperature of junction, by increasing the temperature of junction of SCR, or by also applying very large anode to cathode voltage, right? And of course last one, by increasing, just injecting the small gate current, and this small gate current triggers the SCR and SCR fires. So this is how you can study the behavior of SCR by considering it made up of two transistor. So let us stop here. Thank you so much for viewing this video. Bye.